In this video, I'm going to talk about the Taylor series, and more precisely, how the Taylor series is used to write a function differently. So if we have some function that we can write it as a Taylor series, the interesting thing is if we include all the terms in the Taylor series will be exactly the same as the original function. So here I wrote down what the Taylor series is, and the Taylor series says the value of our function at some location I plus 1, so some location xi plus 1, is equal to the value of the function at xi plus a contribution from the derivative, contribution from the second derivative, and contribution from the nth derivative. And if we include all the derivatives from n is equal to 0 through infinity, this will be an exact representation of our function. That's kind of an odd but maybe interesting concept. So let's look at how that might work in practice. So here I have some axes, and on the axes I'm going to draw some function. And this can be any function we want. Let's say our function looks like this. And then also on the axes I'm going to draw xi and xi plus 1. And at that locations I know yi, and I also know yi plus 1, which exists out here, yi plus 1. And the goal is, what the Taylor series tells us is if we include all the terms in this series, this value for yi plus 1 will be exactly given by this function. So the Taylor series will exactly match the function. So let's see kind of how it works by building up from one term. We're going to start with one term, and then we're going to move to include more terms. So what is the Taylor series if we just include one term? Well, if we just include the first term, so let me erase this red line, and I'm just going to use, say, green to say what the function might look like with the first term. And if we just have the first term, the estimate for yi plus 1 is just yi. We're just including this first bit in the equation, which says with the first term, y at I plus 1 takes the same value as yi. Now, what if we include two terms? I change colors and I use purple to represent two terms. If I use two terms, I'm going to have yi, but I'm also going to include the slope contribution. So I know at this location I, there's some slope here, and I'm going to use that slope and my step size h to approximate what the solution is over here. So this is yi plus 1 using two terms. And let me just write yi plus 1 for just the first term down there. Now, what if I include all three terms? Well, let's do blue for that. If I include the first three terms, then I have the function value at I, the derivative, and the curvature. If I put all that together, I get something that it's even better. Maybe it looks something like that. So this would be yi plus 1, including all three terms that have been underlined with blue. And if you continue this, you can imagine that this point, yi, the actual function value yi, if we include all the terms in the series, the Taylor series will converge to that point. And that's kind of how the Taylor series works. Now, the Taylor series is useful in telling us more information about numerical methods. For example, Euler's method only includes these first two terms, so the purple line, the pink line, and that tells us that Euler's method has a second order local error, and it's a first order method overall. And a more detailed explanation of that is given in a different video. So that was my video on introducing the Taylor series, and hopefully it has explained to you how the Taylor series works and why it works, and now you have a little bit more intuitive background when you see it used elsewhere in this course.